That's the deal.
All right, everybody, let's get started. Let me get the attendance sheet passed around. Okay, so just a quick recap of scheduling and whatnot. You all have your homework 4 due on Friday. I'm going to do something with the example today on the slab design that might seem, I don't know, redundant, but the point I'll make is it sort of references the homework assignment, because as you know, on the homework assignment, the determination of moments is going to be a little different than what we've been doing in class so far. We're not looking at simply supported beams and uniformly distributed loads on the assignment, because there's cantilevered beams, there's point loads, there's all sorts of different loadings on the system. So I'm going to kind of make a point about that, because it might make what you do on the homework assignment a little easier. Now, a couple other things. Engineering Career Day is on Wednesday. It's in the Student Center. It takes place all throughout that morning. I could use some volunteers to help out that day if you're interested. Just let me know. I'm pretty sure we can feed you and whatnot that day, so free food and all that. But we'll talk about that later. I'll go ahead and just make sure it's on everybody's mind, our first celebration of learning. So we celebrate on the 26th, next Wednesday. So Monday, we'll have our review, and you know how I do my reviews. You know, you all come in prepared to ask whatever you want. For those of you that are in steel design, you know we have a review today. Let me turn this off. Okay, sound good? All right, so with that, let's just sort of jump into slab design. We talked about this a little last time, so I want to make sure that this is, that everybody just sort of got their game face on, if you will, about what we're after. So remember, we're talking about, you know, a typical floor system in a building, and we've talked about the beam design, and as such, we've also sort of talked about the girder design, because the girders are just beams with different loads on them, and so between what we've done in class and what you do on the homework assignment, you'll be good there. But we haven't talked about the slabs. The slabs themselves, the floor surface that you need to design. Now again, we're not talking about slab on grade. We're not talking about, you know, the slab that's on the ground in your garage or maybe your backyard patio or something. We're talking about a suspended slab in a building that is designed to hold up load. In other words, we're not talking about like this floor system, because this is on the ground. We're talking about this floor system, the system above our heads, that's holding all the offices and the hallways and all of that stuff. Okay, so that's really what we're after today. Now, remember we talked about the difference between a one-way slab and a two-way slab. In here, we're going to concern ourselves only with one-way slab design. But remember, in a one-way slab, you're assuming that the slab only bends one way. And you're doing that so that you can treat the slab like it's a beam, okay? The beam behavior assumes that it only bends in one direction. Whereas if you were looking at two-way slab design, I'll just say this, the math gets a little more tricky, gets a little more complicated. You can shave some weight and some thickness off of the slab if you go with a two-way slab, but and we talked about this last time, but I'm not really going to worry about that for the purposes of this class. If you're interested in that, that is definitely like a concrete design 2 or something that you would do in grad school is two-way slab design. Okay, all right. This is really sort of the meat of what we're talking about today. So we're going to be doing a slab design, and we're going to be assuming for our slab that, you know, basically what we're going to be doing is designing the reinforcement for this little itty-bitty beam right here. We'll design the reinforcement for a strip of slab. We typically assume that strip is 12 inches wide, so it's a foot wide. And we figure out how much reinforcement needs to go inside that 12-inch strip, and then we just repeat it across the board for the rest of the slab. So it's like you can design this little bit, just use that pattern over and over again, and there's the reinforcement for your slab. Now, we will have 2 layers of reinforcement. So we'll have the main steel, which goes along the span, and its purpose is to resist the load, actually hold up the slab under the forces. So, you know, again, we have a floor system up here. So the main steel is what's going to reinforce the slab against failing under, you know, the offices and the chairs and the people and all of that. But we also have our temperature steel, because remember, slabs are inherently thin. And because they're thin, under thermal expansion and contraction, they will want to crack. So we have another layer of steel in there just to prevent the system cracking under thermal expansion. And there's not really a whole lot of design with that. You just sort of compute what you need. It's pretty simple. Now, like I said, this is like I said last time, this is a known cross-section problem. Remember, known cross-section problems are a lot easier, okay? Because you don't have to figure out what the beam looks like. You kind of already know what it is. And that might seem a little counterintuitive with the slab design, but you know how wide it's going to be because you're assuming a 12-inch strip, so you know the width, and then you know the depth as well. You know the depth because we end up using just minimum thicknesses from ACI anyways. So if you know the height, you can just take the height minus 1 inch for cover, and boom, there's your depth. So you know the height, you know the depth, you know the width, you know the cross-section. So the process for determining determining your required reinforcement is a little more straightforward. So what's our procedure? Step 1, we compute the factored moments on the beam. One of the things I want to tell you right now with slabs, because this is really easy to think that you might be doing something wrong. Whenever you're looking at slab problems, the actual values of your moments, like the actual magnitudes, are pretty small, okay? So we've been doing beam designs, and we'll design for a moment of 300-foot kip or 250-foot kip or something like that. But for a slab, when you're looking at that strip, it might be a moment of like 3-foot kip or 4-foot kip because it's such a small slab or such a small strip, and there's just not much load on that individual strip. So, but again, the slab itself is really small. So it's like you're dealing with really small moments, but you're also dealing with a really small section. So it all balances out. Now again, we don't need to assume the cross section because the width is 12 inches and the height is our minimum height from ACI. We do assume that phi is 0.9, so that is something we would need to go back and check, but that usually isn't an issue for slab design. We compute our row value for design purposes. Now remember, the formula that you see here, this isn't the just pick a row value out of the sky formula. This is the solve row formula. In other words, we derive what row is in order to achieve a given moment demand. So we're not guessing a row value here, we're solving for one. And so I think that's a really important distinction to make. Once you get that, you determine your main steel as row BD and your temperature steel as 0.0018 BH. Okay, that's not a typo. This is BD and that's BH. That's really easy to mistake. Okay, your temperature steel is just looking at the slab as a whole, ensuring that it doesn't crack under thermal expansion and contraction. But your main steel is based off of capacity, and you should know by now that when we're looking at capacity, we really care more about that D value than we do H. So that's sort of, I guess, a reason for why those two are different. Then we choose a reinforcement pattern, which, by the way, I showed you all this guide last time. We're going to use it today. I printed off a few so that everybody would have one. Here's that. Here's that. Here's that. If there's an extra, you can have it. All right. Sound good? Okay. The only other thing that might be new, I would think, with the slab design, other than the structural analysis, which will be a little unique, is this part. Whenever you pick a reinforcement pattern, you're going to be repeating that pattern throughout the slab. So you actually need to check and make sure that your spacing is appropriate. In other words, let's keep the numbers simple. So, you know, you've got rebar that gets bigger as your numbers get higher, right? So you've got number 3 bar, number 4, number 5, number 6, right? So I might be able to do one reinforcement pattern that's like, I don't know, number 3s at 3 inches, or I might be able to do like number 10s at 24 inches, you know, so, and in the end it would sort of be the same reinforcement because I've got these bigger bars that are spaced further and further apart, right? Now the contractor's probably like, hey, give me the number 10s at 24 inches because that's just less bars on site that I have to handle, right? But think about it. If I have a slab and I have reinforcement spaced at 24 inches, anybody see a problem with that? I mean, that's a solid 2 foot of the slab with no rebar in it. That sounds kind of wonky, doesn't it? Doesn't sound very safe, right? So one of the things that ACI requires is that you have to make sure that the reinforcement pattern that you select meets the minimum spacing requirement. In other words, ACI has limits on how far apart you can space the bars because you want those bars to be effective in resisting the moments in the slab. You wouldn't want your bars spaced out like every 5 feet. You know, you have a big gap of slab that wouldn't have any reinforcement. And so you have reinforcement, main reinforcement spacing requirements, and you have temperature reinforcement spacing requirements. They're a little less stringent because they're not about load carrying capacity. They're just about shrinkage, cracking, and what have you. So far, so good? All right, so let's design a slab, start to finish. Okay, so I got a slab. We're going to say it's a 10-foot slab, but I want everybody to have sort of an understanding of the three-dimensionality of the problem so that everybody understands what do I mean when I say the span length of the slab. Now, we're going to use regular old materials, normal weight 4 KSI concrete, 60 KSI steel, pretty straightforward stuff. I'll put some load on this one. We're going to put a 200 pounds per square foot live load on there. That's pretty heavy, okay? Remember, a library, its live load is something like 150 pounds per square foot. So we got some oomph on this one, okay? So we got a pretty heavy load on there. Now there is dead load on the slab, but the only dead load that we're going to consider is the self-weight of the slab. Okay, now remember, I could put dead load on top of this, right? And so I'd have not only the self-weight of the slab, but I'd have a stationary dead load and then a transient live load. All right? Sound good? Okay. All right. Now, bear with my three-dimensional art skills. I'll do my best here. Okay. Okay. Now, what we're talking about here is a slab that has a span length of 10 feet. Okay? So we're talking about the span length of the slab from end to end of the slab. But remember, the slab goes from beam to beam. Okay? And the one thing to keep in mind is that the span length of the slab is the girder spacing of the beams. Okay? And so let me see if I can draw that out for you. All right, so I've got a slab and I've got these two beams that it's sitting on top of. So here's a beam like that. Here's a beam like that. Okay? But what we're talking about is, so this is in 3 dimensions. That, that, that. Okay, so what we're talking about here in this particular problem is we're talking about a situation where this distance is 10 feet. So our slab, so here are our beams, okay? So those are what we've been designing before, you know, our 12-inch wide by whatever, 27-inch deep, and got 4 number 7 rebar, whatever. Those are the regular old beams that we've been designing, but here's the slab that goes on top of them. And however far apart the beams are, that's our span length for the slab. Does that make sense? Okay. Now what we're after is this. So I'm going to pick out a strip of this slab, and that's what I'm going to design for. Okay? Now this strip is 12 inches wide. Okay? Now, let me look at this cross section. So let's look at it like this. Okay, so I'm going to look on this side of the slab, and what do I see? Okay, so I've got maybe something like this. Okay, and this dimension is 12 inches. Okay? So that dimension here is this dimension. This is just me looking into it. Okay, does that make sense? All right. Now what we're ultimately going to do is we're going to design two types of reinforcement patterns. Okay? So the first reinforcement pattern we're going to design is the reinforcement that sort of goes this way. Okay? That's the main reinforcement. Okay? And when I start laying this out, we're saying that this is going to be H, that dimension is going to be D. That should be pretty familiar notation by now, right? And that's to the main reinforcement steel. But we're also going to have another pattern of steel going crisscross in the opposite direction, going like this, that way. And that's going to be the temperature reinforcement. Okay, does that visually make sense? I know that sometimes when you're looking at it three-dimensionally, it's like you got to kind of take a second and get it in your head. All right. Any questions? All right. If you're okay with that, then let's do this like we have done, pretty much any other problem up until now. And so our first step is always to compute MU. Okay? So let's go through that. Now, help me out. I have a beam, with certain dimensions, B wide, H tall. This problem, the beam doesn't have any superimposed dead load, but there is its self-weight, right? So what do I do there? I've got to compute the load due to its own self-weight. How do I do that? I've got a simply supported beam in this case. It's 10 foot wide, right? And so I'm going to have a distributed load on there that's going to be its self-weight, right? And so it'll be like WL squared over 8 to get the moments. But how do I compute that distributed load? We've done it a few times already.
You got to figure out the area.
And then do what?
And multiply it by the...
You're on the right track.
Load.
Well, no. So ultimately what we're going to do is we're going to compute the self-weight, which is gamma times BH. Right? Does everybody remember that? Okay? So what do we know about this material? Okay? We know that it's unit weight, it's normal weight concrete. So what's our gamma for normal weight concrete? I heard somebody say it.
150.
150, yeah. 150 what? There we go. Pounds per cubic foot. Do we know B? What is it, Mr. Stratton?
It's 12 inches.
12 inches. We're assuming a 12-inch strip. But we don't know H yet, okay? But remember, we're just going to use the minimum ACI height. Because it's a slab, we want it to be as thin as possible. We're going to use H min. So now we got to go back to ACI. We're going to ask ourselves, what is the minimum height for a slab? Well, here we go. So, bless you. So, I have a slab, and we're using regular old material properties, so we don't need to go through and adjust what's in this table for higher grades of steel or lightweight concrete or anything like that. Now, my slab, it's not a cantilever slab, it's not a continuous slab, it's not going, it's just simply supported. So, when I have a simply supported slab, my minimum height is L over 20, okay? So what we're going to do here is we're going to take our minimum slab height to be L over 20, which is 10 foot over 20. But here's the thing. When I divide that out, that's going to give me how thick the slab is in feet. But I don't know, like if I'm thinking about slab thicknesses and beam dimensions, feet really doesn't make a lot of sense to me. So I'm going to convert that. 12 inches per foot. And so what do I get? What we got? 6 inches. All right, so what that tells me is that this slab is going to be 6 inches thick, okay, to support this load. That's a pretty thick slab for a building. I mean, like, I'll go ahead and tell you that the slab up here is probably like a 3 to 4 inch slab. That's pretty thick. But remember, so a couple things about that. We're not taking into account the composite behavior of the beam and the deck. We will do that later when we look at T-beams. We might actually start talking about that today. But two, I mean, we are using these ACI minimums and whatnot. One thing I will say, well, when you look at the reinforcement pattern, actually, let's hold off on that. I want to wait until we get to the reinforcement pattern, and then you'll see. Okay, now, so let's go back to our formula up here. So we have W naught is gamma C BH, and so that's, let's do it this way. Let's say 0.15 kips per cubic foot. Just convert that to kips, and then we have 12 inches, we have 6 inches, but then remember we got to convert that. Remember how we did that? We would say 1 square foot is 144 square inches. So what does that come out to be? .075. Do I have a second on that? Okay, and that's kips per foot. Okay. All right. Everybody with me on that? Okay. So let's just sort of write some stuff down. So we have a self weight, which is 0.075 kips per foot. Then we would have maybe a dead load to consider and a live load to consider. Now for this problem, there was no superimposed dead load, right? So this one is 0. Okay, but what about the live load? What do I know about the live load on this problem? It's 200 pounds per square foot, right? Okay, now help me out with this. Let's say I got a floor system, right? Okay, so I got bam, 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 bam. And let's say I've got that. And let's say I'm looking at this beam right here. If I have 200 pounds per square foot of live load on that floor system, how do I determine the load on that beam? By the length?
It'd be the width.
The tributary width, right? So what do you do? So, okay, you would say, all right, let's take a look at this beam. The tributary width is about like that, right? And so if this dimension is like, I don't know, 16 foot, you'd say that the live load is 200 PSF times 16 foot, right? Remember, you don't multiply by the length because you use the length to say WL squared over 8 to get your moments, okay? But what you're doing is you're taking that distributed, or that pressure load, and you're collapsing it into a single line load on that beam, okay? Does that make sense? So you would take the pressure load times the tributary width for that beam. Does that make sense? Now, here's my question. What do you think the tributary width is for this 12-inch strip? How much do you think that 12-inch strip is responsible for?
Itself. So 1 foot.
That's exactly right. It's going to be responsible for all the floor load above it, right? So I propose that the pressure load, or the live load, is going to be 200 pounds per square foot times a width of 1 foot. Does that make sense? That's a little unique to problems we've done before, but think, what happens when you get outside that 1 foot strip? You're just on the next 1 foot strip, and it's responsible for its own tributary width. Or tributary width, I should say. So when you're doing slab design, the tributary width of that slab is the width of that strip. And it makes the math a whole lot easier because 200 pounds per square foot times 1 foot is just 200 pounds per foot, or 0.2 kips per foot. Does that make sense? Okay. Now, what I'm about to do might seem a little weird, but there's a point that I'm making with this. And the point that I'm making here is directly related to homework 4. So bear with me. Okay? Okay, now I want to show you something. All right, we've got this. So we have a self-weight of 0.075 kips per foot, a dead load of nothing, and this. Does that make sense? So method 1 is what we've been doing this whole time, okay? Which is, we say, okay, let's factor this. And just help me out, what does that come out to be? Remember, we apply our load factors, 1.2 for the dead, 1.6 for live. No superimposed dead, just the self-weight.
.32.
0.32. Do I have a second on that? For this? Hold on. Wait. I got a little bit of a different answer.
I got 0.41.
That's what I got. Anybody else? Did I have a mistake?
Yeah, it's 0.41, I believe.
I think you got outvoted. Maybe check to see if that's a multiplication between the two. All right, and then mu is WL squared over 8, which is 0.41 kips per foot times, what was the length?
10 feet.
10 feet squared over 8. All right, so everybody got an answer for me? Let's do like 3 decimal places on this.
.125 kip foot.
125. And no second. Okay, all right. Now, that's our first method. Okay, the first method is to just factor the loads and then use those loads to compute a moment. Now, the second approach, it's going to seem like I'm doing more work than is necessary, but there's a point I want to make. Okay? Now, what you could do is you could say, let's compute just a dead load moment, in which case it would be WL squared over 8 for the dead load, and then the live load do the same thing. Okay? So let's do each of those separately. Okay? And I know you might be like, what are you doing? There's a reason why I'm doing it. Trust me. right, so somebody give me a dead load moment. We got an answer for me?
0.9375.
Okay, so we'll say like 0.938. And what is that, foot kips?
Yeah.
Everybody has a second on that? Okay, and then the live load. 2.5. Okay? Second on that.
Yep.
Now I want you to factor the moments. 1.2 MD plus 1.6 ML. So did it come out the same? Yeah, it comes out the same. It comes out 5.125. Okay. Now, I'm sure some of you are like, Dr. Mike, you just wasted like 2 or 3 minutes of our time. Why did we do that? Okay? Let's take a second and take all this in. Okay? What do I have going on with the dead load? I have a simply supported beam and a uniformly distributed load, right? Okay, what do I have going on with the live load? I have a simply supported beam, uniformly distributed load. Because those are they're the same. I have a simply supported beam, uniformly distributed load. I can just factor the load and use WL squared over 8. Okay? Now, why am I talking about this? The reason why I'm talking about this has nothing to do with the slab. It has to do with this. Okay? This is your homework assignment. Okay? Dead load. Cantilevered beam, uniformly distributed load. Live load. Cantilevered beam, triangular load. You can't just WL squared over 8 the whole thing. It doesn't work. You have to compute your dead load moment and your live load moment separately and then factor them. Okay? What about problem number 1? I have simply supported beam, uniformly distributed load for the dead load. You can use WL squared over 8 for the dead load. That's fine. But for the live load, if you say, well, the beam's 27 foot long and I got 70 kips on it, so 70 over 27. If you do that, I want you to take your hand, do that. It doesn't work. Okay? You can't just turn this live load into a distributed load and use WL squared over 8. It doesn't work. You won't get the same moment diagram. And if you don't get the same moment diagram, you won't get the same max moment. Okay? Does that make sense? So don't do that. And if you catch yourself wanting to do that, I want you to do that. I'm not going to do it, but you can do that. Okay? So treat your dead load moment and your live load moment separately, and then factor them. Okay? Because I'm going to tell you, it's not WL squared over 8 for the dead load and the live load for either one of these 2 problems on the homework. Okay? Does that make sense? All right. Okay. I went off on my tangent enough. Okay. So regardless, step 1, we have MU is 5.125 foot kips, right? So I can put that down here. I'll just write that down so we have it. Step 1. Okay. And what do we know about our slab? We know that B is 12 inches. We know that H is 6 inches. What about D? We didn't talk about D. Well, whenever you're doing a slab, you can basically say that's the height minus about 1 inch. So you can say that's 5 inches. And the reason why we say the height minus 1 inch is because the cover requirement for a slab is 3/4 of an inch. So that extra little bit will get your rebar up and up to where you meet that cover requirement. So a 1 inch off the height is a good estimate. Okay. Everybody good on this page? All right. So past this, it's going to get pretty rote. This is going to get pretty familiar. Okay? So step 2, we need to compute MN required. And so MN required is going to be mu over our resistance factor. And remember, our resistance factor is a function of the strain in the steel. I have no idea what the strain in the steel is because I haven't picked a pattern yet. So we have to assume that phi equals what? 0.9. And so that's something we would technically have to go back and check. So this is 5.125 foot kips over 0.9. And because I'm going to throw this into a design expression, and that design expression is going to have a bunch of, KSIs and inches and things like that, I'm going to go ahead and convert this by saying 12 inches per foot so that my answer comes out in inch kips. And so when I do all that math, what's that come out to be? So MN required is 68.33 inch kips.
Yes.
Is that a second on that?
Yep.
Okay, good. Now, again, your moments for slabs are tiny. I mean, when those beam problems, we were getting like MN was 4,000 or 40 or something like that. It's okay for slabs that are going to be small. So I'm just telling you that because when you're on a homework or on a test, don't think that you're doing something wrong. If you're doing a slab, the numbers will be tiny. Okay. Step 3, compute our row required. And remember, our reinforcement ratio, that formula is a little big, so take your time with it. Okay, so 1 minus the square root, 1 minus 0.85 FC prime BD squared, 2 MN required. So we were using regular material properties for this problem, 4 KSI concrete, 60 KSI steel. So 0.85, 4 KSI over 60 KSI. Remember, kips and inches, so that's why we converted the MN to inch kips. All right, 1 minus square root 1 minus. Okay, so 0.85 times 4 KSI times, and then what was B? B was 12 inches. And D, we're going to take D to be 5 inches. And remember, don't forget to square that. It's really easy when you're doing these problems to forget to square the D on the bottom. And 2 68.33 inch kips. Okay. We'll say like 5 decimal places for this one. This is a really sensitive number. Because when you're dealing with slabs, you don't have much reinforcement in that little area, so a little bit of resolution on your answer is actually kind of important. So we'll say like 5 decimal places. So I want everybody to take your time with this and make sure that you're getting this right. Anybody have a value? Remember, reinforcement ratios, they are small. So it'll be 0 point something.
0.00393.
All right, I got a second on that. Everybody else getting that? I'm going to tell you, that's the answer. So if you're not getting that, maybe just check your formula. Make sure that you have the 1 minus twice, 1 inside the root, 1 outside. Make sure that you're squaring the 5 on the bottom. 2 times MN. Make sure you're using the inch kips on the moment. But the answer should be 0.00393. Okay? Everybody good? All right. Now, if you're okay with that, what we'll do is we'll say, okay, compute required steel areas. So we're going to have the required main reinforcement, and then our required temperature reinforcement. Now, the main reinforcement is rho BD, but for the temperature, it's 0.0018 BH. Okay, that's easy to miss. Okay, so we have 0.00393, and we have times 12 inches times 5 inches, and then down here 0.0018, 12 inches, 6 inches. All right, and let's get some resolution. Let's do 3 decimal places. You'll see why I want 3 decimal places here in a second. We got one for the first one.
236.
0.236, and that's square inches. Do I have a second on that? All right, second.
0.130.
0.130. Second. Okay, all right. Now, I'm going to label this a very particular way. What's our strip width? Remind me. 12 inches. So this is how much steel is required every 12 inches, right? So I'm going to label this a very particular way. I'm going to say 0.236 square inches per foot of slab. And same thing here. Okay. Now, step 5 is to actually select the reinforcement. Now, in order to do that, the first thing I want to do is look at our main steel and our temperature steel and look at S max. In other words, before we start going off of this chart and figuring out what reinforcement pattern should we use, I want to see what we should cap our spacing off at. Okay. Now I produced this chart for, I think, what was my maximum spacing? Was it 18 inches? I mean, we could produce charts with spacing well beyond that, but you'll see why I limited it to 18 here in a second. Now, let me go off my slides because I want to show you where I'm getting this. Okay, so main reinforcement. The maximum bar spacing is the lesser of 3H and 18 inches. Okay, for maximum bar spacing for temperature reinforcement, it's the lesser of 5/8 and 18 inches. So you're going to see, what was our H for the slab? 6 inches. Okay, so this is going to be the minimum of 3H and 18 inches. This is going to be the minimum of 5H and 18 inches. Now, can anybody just look at this and tell me what this is going to be? It's going to be 18 inches for both. Okay. In other words, whatever option I pick, I have to pick a spacing that's 18 inches or less, which is fine because that's the maximum spacing reported off our chart. However, if we have a slab that's thinner than this, like if we had a slab that's, I don't know, 4 inches thick or something like that, we might have to make sure that we were cognizant that whatever bar pattern that we picked was limited based off of our spacing and whatnot. So just making sure that you're keeping in mind with this. Okay, now let's look at our main steel. Okay, now I'm gonna walk you through this the first time. Let's start off with the smallest bar, okay? Remember, slabs are thin, so thin concrete elements, we don't really need super massive bars. So let's start off with number 3 bars. I want you to help me out with something, okay? If I was using number 3 bars, and I need to produce at least 0.236 square inches of reinforcement per foot, how far apart should I space them?
5.5 inches.
5.5 inches. Does everybody see that? Okay, and notice how I wanted this to 3 decimal places so that I know that 0.24 inches is above that. So this is an option at 5.5 inches because the area is 0.24. What about number 4s? Is there an option for number 4s? Anybody found something?
I think it's 10 inches.
10 inches. Does everybody else see that? Now, why did you pick that? What's the area?
0.24.
Interesting. 0.24. Okay. Now, let's ask it this way. Whenever you've got a reinforcement, like a bunch of different options, which one do you pick? The one that has the smallest area, right? Let me ask you this. Are there any other options, number 5s, number 6s, anything that has a smaller area? Nothing, right? So I got those 2 to pick. Now I got a problem. They're the same area. Which one do I pick? If they're the same area, then it would technically be the same amount of material, right? You're buying the steel per pound. So the material cost would theoretically be the same. So material costs don't matter. Why would I pick one option versus another?
You will use less bars.
Why does that matter?
I don't know. You can go faster, work to go faster.
That is exactly right. If I'm on the site and I'm tying rebar, it's a whole lot easier to tie bars at 10 inches on center than it is to tie bars at 5.5 inches on center. It's less labor hours that go into the actual tying of that rebar mat. So whenever you have options that are the same area, choose the one that's going to have the least number of bars. Use that one, okay? So that is definitely the one that you would choose. That's exactly right. Okay? Now we can finish this out real quick. Let's talk about the options for the temperature steel. Are there any options for number 3s? Any options for number 3s for the temperature steel?
Yeah, 10 inches.
What is it?
10 inches.
10 inches? What about number 4s?
18 inches.
18 inches. And which one would you, they're both the same area, aren't they? And so between those, what would you pick? The number 4s, exactly. So number 4s at 18 inches. And I believe that area is 0.13. Right? Pretty straightforward. So, there's your, if you want, what's your answer? There's your answer. Like here, here's your answer right here. So, we have a slab. You know, assume going on forever on both sides, right? And so we've got main steel, right? Number 4 is at 10 inches. Number 4 is at 18 inches. This dimension, 6 inches. That dimension, 5 inches. Why do I say that's a trial design?
Still have to check your assumption.
So we have to check our assumptions, we have to check our efficiency, what else? ACI requirements, exactly right. So efficiency, ACI requirements, check your assumptions. One of the things I'll tell you with slab designs is that your efficiencies tend to be really high, like 98%, 99%. They because of the nature of the problem, usually you're fine like with verifying your assumptions, but they're really, really high. But checking, you know, ACI requirements on steel and whatnot is probably not a bad idea just because of the nature of the problem. And that's how you design slabs. Yes, sir?
So is, if the area of the steel was different, is it always the determining factor over the spacing?
I would say so, but I would for our purposes in this class, yes. But I don't want you to think, well, that's what we always do. A smart designer, a smart contractor, a smart fabricator is going to look at material prices and look at labor rates and figure out what makes the most sense, okay? Sometimes, maybe I just bump that up to number 5s or number 6s or something in order to ensure that it's less bars to tie on site. Now, one of the things you will run into though is, like, take the patterns that we've got here. If you start saying number 5s or number 6s, you probably start spacing it out further. But remember, your maximum spacing is 18 inches. Now that's a requirement. You can't start shirking that. ACI requirements specifically dictate the maximum spacing is 18 inches. So whatever you do, you got to hold that. Does that make sense? So that would sort of be my best answer is for us, whenever they're equal, go with the fewer bars, but otherwise go with the one with the minimum area. But when you get out of here, use some common sense, looking at your labor rates, looking at your material prices, and see what's actually going to result in the least cost for the project. That's a good question. Any other questions? All right, next time what we're going to do is, well, first off, let me say one, I know we're running out of time, but that is it for exam 1 material. Everything from here on is exam 2. What we're going to do next time is we're going to ask the question, what happens if we treat the beams and the slabs as if they were cast together? We've been treating them as 2 separate pieces. What if we consider them integral? And so that's looking at T-beams, where you have a beam and part of the slab as the flexural element. That's a little bit of a protracted discussion. That's going to take some time. So I'm just going to stop there, and we will pick this up on Wednesday. Don't forget your homework's due on Friday. That's all I got.